this x is really 5.2 because the percent is just a label. Everything here is in percents. So all these are percents. So 5%, 5.2% would just be, in terms of x, would just be 5.2. Okay, so I'm going to go ahead and take a look. You can go ahead and take a look at, let me share my other, I guess I have to share my whole screen or else I won't be able to. Yep, I'll do that, that's fine. Okay, so let me remove this one. We're done with that one. And we're going to start in on what we're doing today, which is our workspace annotation. And today we're going to do quiz 10.1, 10.2, and then we're going to do 11.1 goodness of fit test. You have 10.1 due tonight, along with Project Lab 5. It's late, but okay. Full credit tonight by midnight. Just turn it in tonight, or even by like 7:30 in the morning. It's probably fine. Just get it done tonight. And then Thursday you have Connect Math 10.2 due, and then next Thursday you have 11.1 due, and also Project Lab 10 will be officially due next Tuesday. I think what I'm going to end up having to do is probably just make a video to show you guys how to do that. And then you can just watch it on your own whenever you want and just do that lab. It's not a hard lab. It's a very quick, easy lab. It's super, it's not, there's a couple little things to it, but that make you think, but not very many. So it's not too taxing. All right. Review of Chapter 10.1. Correlation is seeing if there is a relationship between variables, and regression talks about what kind of relationship that is, positive or negative, linear or nonlinear. And then these are the things we're looking at in Chapter 10, right? These questions. Are two or more variables related? If so, how strongly are they related? So looking at our R to see if it's close to -1 or close to 1. And then what kind of relationship exists, positive, negative, and what kind of predictions can be made from the relationship. All right, so scatter plots. Right, so that's when you have your x here and your y there. The y should always start at 0. Sometimes you'll see a spot where like they have this little zigzag here, that goes right in there, and that's if they have to jump for some reason. They feel like they really can't show the data well without jumping from 0, to a different number. But then they should give this little squiggly line here along the y-axis, so you realize that it didn't start at 0. There's this kind of weird thing going on, and it goes from 0 to and then jumps to 60 and then goes up from there or something like that. Okay, so your x's are here. These are your independent variables, the ones you theoretically have control over, and your y's are here, the ones that are that are dependent that you theoretically do not have control over. And then we have rho. Again, rho is written this weird sort of swoopy sort of P, right? You just kind of do this with it, right? It's not like a P where you do a whole with a little number up here, right? It's just a whole little, it's not like that, it's just a swoop right around. So it's just like that. That's a Greek letter R, so it's rho. That's the population correlation coefficient. And then you have regular ordinary R, which is our sample correlation coefficient. And we're going to be comparing that to our critical value from the PPMC table. So PPMC table is where we're going to get our critical values for this problem. Correlation. So we have, if there's a strong positive correlation, linear correlation, then it's going to be close to +1. If there's a strong negative linear correlation, it's going to be close to -1. So our correlation coefficient goes from -1 to +1. +1 is this perfect line with a positive slope. -1 would be a perfect line with a negative slope. And then 0 is when there is no relationship at all. And it's kind of nice because the +1 sort of looks like a line, right? If you kind of tilt your head sideways, it looks like a 1. And this one here, if you look at the slope, it looks kind of like a 1 as well, a -1 or a 1. And then if you kind of look at this kind of a whole bunch of dots just randomly sorted, it looks kind of like a ball, right, or a 0 kind of in a way. So it kind of helps to kind of think of it that way. So this is going to be the first thing you guys are going to do. So take a look at this. This is going to be a problem similar to a problem you're going to get on the exam. Very, very similar. It's 4 points. It's 4 easy points. Just have to match up numbers with their correlation number. So once you guys take just take a couple minutes. I'll give you guys 45 seconds on your own, and then jump in with your group real quick. I'll open up the rooms for just a minute. So 30 seconds on your own. Try to figure out what numbers go with which ones. Maybe take a picture of it if you need to. I'm going to open up the rooms. And I'm going to close the rooms in like 30 seconds. I'm going to close the rooms. So make sure you get in there in the next 30 seconds, or else I'm going to close them up and you won't be able to get in. Just check in quickly. All right, so which one of these is 100? So private chat, which one is 100? Which one of these pictures is 100? Do it in the private chat. Private chat. So it looks like 7 of you have replied. So I'm getting a mix. Some are saying the first one, some are saying the third one, some are saying none of them. Okay, so here's the deal. Correlation coefficient goes from what to what? Goes from -1 to +1. You cannot have a correlation coefficient of 100 or 50 or 5 or 2. None of those exist. Those are impossible. They don't exist. So you cannot have those. A perfect line is a correlation coefficient, if it's positive with a positive slope, is a correlation of 1. So this is your 1. A perfect line with a negative slope would be a -1, and then if you have no correlation whatsoever, just a big giant blob, it's a circle, it's 0. And then let's see, these two are the positive ones here. So this one looks more like a line, I'd say. So that one would be it's between 0.6 and 0.8. So since this is more like a line, which one's more like a line, 0.6 or 0.8? 0.8. So then this one's 0.6. And then between these two, this one's more like a line. So that should be closer to -1. So that's going to be -0.8. And this one will be -0.5. Okay. So again, this is going to be the easiest, probably the easiest 4 points you're going to get on the exam. So just Yeah, make sure that you don't mess those ones up. Okay. So here it is again, the numbers. All right, now sample correlation coefficient. How do we calculate this R, which can be between -1 and 1? Well, you can use big long formula, but we're not going to do that anymore. Instead, just put your X's into list 1, put your Y's into list 2, and do stat test ln reg t-test. That'll give you your R, it'll give you your A and your B, it'll give you all sorts of great stuff. It'll give you your p-value as well, and lots of other stuff I've noted that was, but, okay. So, for a second I thought we were getting bombed. All right. Now, again, stat ln reg t-test, it'll give you your A and your B. See, there's the B. It'll give you your R. So that's where you find it there. So here are the steps. First step, hypothesis testing. H naught is always equals, because it's always null hypothesis is always no. No difference, right, equals, no line, no correlation. H naught is always the no's, no line, no correlation. So H naught, if we do not reject H naught, then it is not a line. Right? If we accept H naught, if we do not reject it, then it's not a line, no line. You got to keep those together, because people screw this up all the time and they get mixed up on how that works. So that's how that works. What it's saying is you have a bunch of random dots. It's not a line. H1 is saying that rho is not equal to 1. It's closer to 1. Rho is not equal to 0. It's closer to 1 or -1. So there is a significant correlation. In other words, it is a line. So that's what H1 is saying. H1 is saying that rho is a line. It's close to 1 or -1. So in other words, if we reject H naught and say that H1 is correct, then it is a line. Rejecting H naught says it is a line. So make sure you kind of really wrap your head around that. So I'll give you guys a second to stare at that and make sure you get that down straight. Write notes that you need to, because it's important. Understanding this part is going to be worth probably about 10 points on your exam. Out of 200 points, that's about 5% of your exam. It's not, not a lot, but it's not much to, it's important to kind of straighten out for that 5%. It's 5%. That's like half a grade. Okay. So our critical value is our second step, right, using the PPMC table. So degrees of freedom is n minus 2 because we have two variables. So if I had, say, seven points here, then I would do 7 minus 2, which is 5. And looking along here, and then my alpha is 0.05, then I'd grab this one and I'd grab 0.754. So what you do then is you shade. You draw a line. It's similar to the normal line, which goes like this, except for it's just a straight line. And so you just do a straight line, and then you put in your 7.54, and you shade between there, and then you do a negative sum one as well, because remember, these chapter 10s, they're always two-tailed. Always. It's always going to be a line, and you don't care if it's positive 1 or negative 1. It just needs to be close to one or the other. So you can have a negative 7.54 as well, and shade to -1. So those are your rejection regions, rejecting H naught and saying it is a line. So here, remember, 1 is like a line with a positive slope. -1 out here would be a line with a negative slope. Okay, good. So this is your problem you guys had. This is about what your scatter plot should look like, more or less, roughly. Right, your x's, your amounts are along the bottom. It should go at least cover from 1 to 7, because that's as far as your x's go, or 1 to 6.5, I think. And then your y's should cover up from 0 up to 5 or 6, up until your data you have there. So it should look something sort of like that. And here we go. So step 1, H naught is rho is equal to 0. H1 is rho is not equal to 0. This is going to be true always for chapter 10. All of chapter 10, this is going to be the case. So that's what we're going to be using. Our critical value, look it up on the table, it's going to be, let's see, my alpha is 0.05, I think, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items. So 12 minus 2, my degrees of freedom would be 10. So looking along the 10, degrees of freedom 10 along this row here, alpha 0.05, it's going to be 0.576. That's going to be my critical value. So you're going to make a line and put in 5.76, shade out to the outside, negative 5.76 and shade to the left. And those are your those are the numbers there. Let's see if I can make that better. I don't think I'm going to make it any better. I think I'm just going to make it worse is my guess. And so then we're going to go ahead and put our data into our list 1 and list 2. So put your X's into list 1, put your Y's into list 2, and then you're going to do stat calc 1 var stats. And you should end up with an R of 0.941. So 0.941 goes right here. It's between 0.576 and 1, so it's holding the rejection region, right? So we're going to reject H naught. So chapter 10 is always going to be two-tailed, always, because we don't care whether it's negatively correlated or positively correlated. We just care that it is correlated. So we don't care whether it's on the negative side or the positive side. And then you're going to find it's weird. Chapter 11 is always going to be right-tailed, always. So they're a little bit strange. But chapter 10, always two-tailed. All right, so R, we found that using Lin-Roche t-test, L1, L2, and then we're going to reject H naught. Don't forget the H naught. Some of you guys left that out and you said reject, and you lost a half point every time you did that. So that's going to add up to, like, you know, a couple points on your exam just for writing an H naught. Why wouldn't you just write an H naught and say and get those 2 points? And then step 5, it is a line, right? Because we rejected H naught, so it is a line. That's what rejecting H naught says. See, it's totally close to 1, which is a line, perfect line. So it's a line. There is enough evidence. We rejected H naught, enough evidence to say there's a correlation between drug amount and reaction time. That's all you need to do. But there is a correlation between drug and reaction. Okay. So you guys stare at that for a minute. Maybe I'll type in something prettier here. Lin-Roche t-test, linear regression, linear regression, not linear regression t-test of L1, L2.
Professor?
Yeah.
Yeah. Do we use the X, the 5.2 for anything in this?
Yes, we do. Down below. We're not done yet. So let's move on down, and we'll take a look. So we want to predict.
Professor?
Yeah.
For number 5, the summary, do we have to always say if it's a line or not?
No, you don't have to say it's a line, but the line will help you because the line leads to this down here. So if you say it's a line, then when you find your linear correlation line, your regression line, so this is y equals a plus bx, right? So you grab that from your calculator, and you said, oh, my a is 0.01793, and my y is 0.6371. So my linear regression line is y equals 0.0193 plus 0.6371x. Okay, so now the question you guys were asked was, if x is 5.2%, then what would be my reaction time? What would be my y? What's the y that goes with this x? That's the question. So percentage, you always get the percent. And 5.2% is that your x or your y, and you figure out it's your x. So you figure out what your x is, and then you put that in for x to figure out what your y is. So I substitute into my x, and I got y is 3.33 seconds. So when we have 5.2% of drugs in our system, our reaction time will be 3.33 seconds. Questions on this one? Okay. So we're going to go ahead and take a look at, and then again, this is the limit t-test, and this is kind of what it looks like, right? You put in L1 for X, you put in L2 for Y, leave the frequency at 1, and then leave it as not equal to. It's always going to be not equal to. This reg EQ, I'm not sure what that is, just leave it alone, and then hit calculate. Do you guys want me to show it real quick on the calculator? Here, I'll do a quick demo while we've got it, got everything here. So I'm going to do stat, edit. You're going to put your data in to list 1, whatever that might be, 24, 21, 22. Okay, and then you have, double check your data, make sure you didn't mistype it, because if you mistype it, then you don't even know that you've messed up, and you've messed up. All right, so double check your data first, because you screw this up here in inputting, everything's wrong. And I don't know how to grade it because I can't give a partial credit, right, on the calculator. I don't know what you've done. So, so double check your numbers really carefully, make sure you input them correctly, and then you're going to do stat, tests, and again, you're going to arrow up, because linear reg t-test is on the bottom. It's not interval, it's a test, linear reg t-test. This is a hypothesis test. And so you're always going to have L1 for X, Y is going to be L2. Leave the frequency as 1, you only have 1 of each. This is always going to be not equal to. It's always going to be this for these chapters. And then reg EQ, leave that blank, hit calculate. And it will give you, again, it tells you your linear regression line y equals a plus b, x up here. Gives you your t-value, gives you your p-value, right? So this is 19% likely, which means we should not reject. Right? It's pretty common. 19% is not unusual at all. So I think we did not reject, which is good. 2 degrees of freedom is 3. My alpha is 1.8, or 8, oh sorry. So this is a totally different problem. I have different data in there, so yours is going to be different. But gives you your alpha, gives you your beta, and then gives you an R. So that's, those are the things you can get from there. Yours will look different because obviously you had different data in yours. All right, so regression line. Let's talk a little bit about that just to kind of refresh people's memory on that one. It's the line of best fit. So you can draw several lines through your data, and the line that fits it best is what we call the regression line. And by fitting it best, what we mean is that we take the distance from every point up and down to that line, and we square all those differences, and then add them up. We sum them. The one with the line with the smallest sum wins. That's your line of best fit. That's your regression line. And it used to be really hard to calculate, but you can just do that with the calculator now. With it calculates it for you. It just gives you that whole it gives you the y equals a plus bx, and it gives you the a and the b in the calculator. Okay. So why am I reading? Haley, please read. Can you read the stuff that's typed out in red and blue?
This line is used to predict the values of y for a given x, only used when there is a correlation relationship.
Great. Hold up for just a second. So again, hold up a second. Hold up for a second. So again, only use this line. Here's my line, y equals a plus bx. Only use it when you have a line, when your data is line-like, right? When your data is a bunch of dots and randomly assorted. So when you reject H naught, when it is a line, then you can use this formula. Okay, keep going.
When R is not significantly different from 0, the best predictor of y is the mean of data values of y. If not a line, use the average y. Do not reject H naught.
Yeah.
Y equals R.
Right. So in other words, if we do not reject H naught, then it's not a line. When it's not a line, because we didn't reject H naught, and it's closer to 0, then just use the average. Y is y bar. Use y bar for y to predict. Right? Because we all know, like, well, I'll talk about it in a minute, I think. So how do we get the regression line? Again, y equals a plus bx. Using your TI calculator and lin-reg t-test, find a and b. And a couple quick comments. One is you really shouldn't go too much further beyond your current predictions. So let me stop sharing for a minute. Right. So, you know, say I had data from 2000 to now, 2000 to 2020, and on cell phone usage. I really should not use that to predict something that's going on in 2050, because that's all sorts of things could happen between now and I'm only basing off 20 years here. I should predict something that's 30 years away off of these 20 years. You know, all sorts of things could happen between now and then. But I could probably predict something that will happen 5 years from now, or maybe even 10 years from now. But, you know, 30 years out is kind of far. If I want to predict something, you know, 40 years out, I should take data maybe from like 1800 to now. I can look at population growth from 1800 to now, and then I might be able to predict 50 years or 60 years in the future, maybe even 100 years in the future. But you shouldn't go too much further than where you're outside of beyond your kind of your data. You know, so you shouldn't go, you know, maybe if your data goes X amount, you shouldn't go 5 times that in the future. Okay. The other thing to comment on is, again, reminding yourself if your data is not correlated, right, so you did not reject H0, then the best predictor, if your data is not correlated, then the best predictor is the sample mean. Right? There's no correlation at all. Right? So for example, height and scores on the test are not at all correlated. So my best guess at somebody's score on the test is the mean score on the test, because there's no correlation. It's not based upon their height. I wouldn't say, oh, well, you're really tall, you must score really high, or you're really short, you must not have scored well. So again, here's another example of it. So here you can see the blue dots. It's just a bunch of random dots, right? I will get a line for it. Here, this is my line. Oops, you can't see it very well. This is my line right here for it. It's going up slightly. But if I just remove a couple points, if I just take these 2 points out, then all of a sudden, my data is going down a little bit. And so you've gone from something where you have this upward slope to now it has a negative slope just by removing a couple points. So it's kind of crazy. You know, obviously you shouldn't put much stock in any of these, you know, in these lines if your data is not correlated. So here we would have had a correlation close to 0, so it's not a line, which means that you should just use this straight up down, this average here, this red line instead. You should just use the average. That's your best guess. All right, here's another point. This is really cool. This is this kind of nifty little problem where someone pointed out that these 4 different slides all have the exact same R value and the exact same y equals a plus bx as well, I believe. And you can see that, you know, this one totally looks like a line. This one looks like it might be even slightly different, but because you have this little outlier that's kind of affecting it, maybe your data should be kind of more along here. And this is totally not even a line. And this is going straight up and down, right, with one outlier out there. So it's just kind of funny how these things are like that. So maybe what they're saying is maybe what you should do is look at your graph and kind of confirm with your graph that it really does match up. And the way you do that is you have your data, right, in your slots, and then you do second stat plot, turn this on. So right now it's off. So I'm going to hit enter to get into 1, and I'm going to turn it on. So I'm going to hit enter on the on, and now it's on. And then I can hit scatter plot, list 1, list 2, and then to get my plot, I hit zoom, which is right here in the middle, top middle, zoom 9, and that gives me my scatter plot. It's kind of cool. And not that important. We're not going to have you do it on the test, but I just show you that anyways, just for interest. Okay, so here's our quiz problem 2. Did you guys need some more time to go over quiz problem 2? Let me show you the basics. So you should have this so far. H0 is rho is equal to 0. H1 is rho is not equal to 0. And then your critical value, you look it up on the table, it should be 0.754 because you have degrees of freedom of 7. There's 7 of these minus 2, so degrees of freedom 5. So again, draw your line, shade 0.754, shade outwards, negative 0.754, shade outwards. So what I'm going to do is I'm going to let you guys go back into your groups, and I want you to work on this one and work on the very last thing of Chapter 10, the very back page of Chapter 10 notes is lab problem 6. So lab problem 6 looks like this. Let's say 10 minutes to work on these, and then we'll take a break from 8:30. Well, I'll give you guys 12 minutes. So 8:35 to 8:45. We'll take a break then. So go ahead and do these. Someone else pointed out that in the p-value, remember if you get this answer, if you get it for a probability for a p-value or any sort of probability, if you get a number larger than 1, then you darn well better have an E negative after it somewhere, because this, you can't have 514%. It's E negative 6, so you're going to draw 6 zeros, and then your number, 51409, and then your decimal place goes after the first 0 right there. Okay, so I'm going to open up your groups, take a break, work on these, and take a break from 5:35 to 8:35 to 8:45. So break from then to then.